Hello there, functions folks. The lesson is on IROC problems, um, instantaneous rate of change, and this is the last lesson of this huge uh, unit zero, as we've been calling it, preview to the whole course sort of unit. And hopefully you already know when the test is. We'll probably have a couple of days for review or a day and a half of review, but we still have to get through this last lesson. The 3-minute review is taking up some homework from last night. So if this sheet does not look familiar, you should immediately stop the video and try this sheet. It's about 10 minutes worth of work, and give it a go, and then we'll take it up. And I'm going to take it up right now. So what you're asked to do, yesterday we talked about instantaneous rate of change. If we were given a table and if we were given a function, it was easy. But what happens if we're given a graph? Well, drawing a tangent is a little bit of a task. Basically, we know a tangent is two things. It touches the graph at one point, but it has the trend of the graph. So for instance, the very first task we were asked to do is to draw the tangent to this graph, and this is the sine graph, maybe stretched a little bit, but it's a sine graph. We're not given the equation. That's on purpose. But we're asked to draw a tangent to the graph at 0.5 seconds. So we see the point of tangency. So, well, why don't I just draw it like this? There, it touches the graph only in one spot here. Isn't this a tangent? Well, it doesn't have the general trend of the graph, right? If I were to zoom in real close, um, and look at the graph, the line and the tangent line and the graph should look very similar. And if you zoom in at that point, they do. So it's a little bit of a task trying to sort of figure out how to get a point of tangency. And you kind of wiggle it around a little bit and so on. And then once you draw that line, then you use your grade 9 skills to calculate the slope, right? You just pick 2 points on it, calculate the rise and the run, and I got mine to first one to be about 0.9. And you repeat this over and over again and ask you to answer some questions as well. One thing I want to mention, and it's easier to see for the second one for me, when I did the slope at 1 second, where that was later on. But if you see it here, when I drew my tangent, what I did is I constructed a triangle that had a run of exactly 1. So, well, why would I want to do that, have a run of 1? Well, then the rise is what the slope is then, right? If the run is 1 down here, the run is 1, then the rise is the same as the slope. So that's kind of a clever way to help yourself with slope calculations. And then blah, draw a tangent, calculate the slope, draw a tangent, calculate the slope. And then they ask, which is kind of a funny thing, to fill in all of the slopes. Fill in all the slopes. And in fact, this is something that comes up more in calculus, is this idea of the IROC as a new function. But getting ahead of ourselves here, they ask for some specific values and ask for you to think, and hopefully you had a chance to try this in class, so you could discuss it with partners and so on. But you can see my answers there, and you're welcome to fill in the blanks where you need to. One last thing that I'm going to point out is this J. This is something weird happens at t equals 3 seconds. So t equals 3 seconds is right there. Notice that what happens when I drew the tangent, it's kind of like part of it, the graph was below the tangent, and part of it, it was above the tangent. Where for all the other tangents, it was either below, the graph was below the tangent, or over here, the graph was above the tangent, right? I draw a tangent here, and the graph is above the tangent. But for this 3, it kind of splits it in half, right? It's still got only 1 point that it touches at, and it has the general slope of the graph. But what's weird, it's kind of like the graph. I know there's a 0 there. That's beside the fact. I'm talking about the rate of change. It goes from being this is a hill to a valley, or from a frown to a smile. And this point is a pretty special point in mathematics, and we'll get to it more when we do calculus. It's called a point of inflection, a point. And we won't talk too much about it, but it is at 3 seconds also where the speed of the pendulum was the highest. Okay. I also said from a downy to an uppy. So that was a downy, this is an uppy, and that's the point of inflection right there. Again, if there's anything else you want to ask about this page, we can ask in class or discuss with a classmate or me, of course. On with the last lesson of the day, and this last lesson of the unit, and this is on a handout, so you can just fill it in as we go. And I think it's mostly concepts we've talked about, maybe in a little more detail than we have in past. So we're asked to draw a sketch that matches this verbal description, and then of course there's space for us to add some more points in here. The expectations today are to sketch graphs that represent a relationship involving a rate of change as described in words. So in words, what's going on, let's talk about the rate of change after. Then we use rate of change to solve problems, including those that arise from real-world applications. All right, so what it says, D increases quickly at first and then more slowly. So D is increasing, so it's going up fast at first and then more slowly. So it's kind of like this curve, right? So D increases quickly at first and then more slowly. So I could say that D is increasing but at a slower and slower rate, right? D is increasing at a decreasing rate, if I wanted to think of it that way. So if the distance is decreasing at, or D is increasing rather, at a decreasing rate, means the distance is still going up, but not by as much as time goes on. So what's going on with the object means it's slowing down, right? Because the distance is changing at a slower rate. So that means also we can say that the speed is decreasing. And that makes sense, by the way, from what we know about instantaneous rate of change. Think of the tangents here. Tangents for a distance graph would be the speed, right, the velocity, where over here the tangent is still positive, so the distance is increasing, but the speed, the instantaneous rate of change, isn't as big. All right, well, we got 3 more to do this. If you'd like to sort of pause and give them a go yourself, you're welcome to. Otherwise, you're along for the ride, and that's fine. D decreases slowly at first and then more quickly. So D is decreasing, so it's going downhill, slowly at first and then more quickly. Slowly at first and then more quickly. Slowly at first and more quickly. So what can we say? D decreases, it's decreasing, but faster and faster. D decreasing at an increasing rate. So you're thinking, okay, what's going on with the speed? Well, if it's decreasing at an increasing rate, that means the speed is increasing, isn't it? Going faster. Okay. D decreases quickly at first and then more slowly. So D is decreasing, but quickly at first, then more slowly. Quickly at first, then more slowly. So D is decreasing, obviously. Decreasing. But at a decreasing rate, since the rate that the distance is going down is slowing. And so what can I say about the speed? The speed is decreasing. Right? Over here, D increases slowly at first and then more quickly. Oops. Slowly at first and then more quickly. So it's increasing slowly at first and then more quickly. Slowly at first and more. So D is increasing. Increases. I'm getting sloppier as I go here. Increases, but slowly at first and then more quickly at and increasing rate. So what's going on with the speed? The speed is increasing. So notice just the words about the change in distance gives us something about some other value, which is speed, which is a rate of change. Okay, what's the next example we got going here? Ferd starts jogging at a constant rate. A bee starts following him, so he starts sprinting as fast as he can. He gets tired, throws up, then walks slowly home. Poor Ferd. Draw a sketch of the speed versus time and the distance versus time. Okay, no problem. So this is just a sketch. We've got no numbers. So your estimate is as good as mine. There would be some things that we want to make sure are consistent. Speed versus time. So speed goes on this axis, time down here. He's jogging at a constant rate. So constant rate, let's say he's jogging along here, right? The speed is constant. Speed is constant. B starts following, so he starts sprinting as fast as he can. So he's at top speed. Now notice, he's not going to jump to top speed straight off. There's going to be an instant of time where, you know, he gets up to speed, right? And again, this is the idea of a function. This can't be vertical. There's going to be a little time where he's increasing his speed, and then he's sprinting. He gets tired, throws up, and then walks slowly home. So when he gets tired and throws up, what's his speed? Well, his speed would be 0, right? So right here, and again, it would take him a little time to slow down, right? So this is when he gets tired and throws up. And then he walks slowly home. Now I'm going to say something here that's a little bit weird, but his speed walking slowly home is certainly less than his jogging speed, so it'd be something like this, right? And I'll come back to this. There's something weird going on here that maybe some of you who are sharp can point out right away, but we'll get to that after we do the distance one. We're going to come back to this little cloud here. But that looks okay. Speed, jogging at a constant rate. B starts following, sprinting, tired and throw up is a velocity of 0 or a speed of 0, and then walking slowly home. All right, now what about distance? Okay. So when he's jogging away from home, the distance is increasing at a constant rate, right? The speed is constant, increasing at some constant rate. So there's his jogging, right? Because the distance from home is increasing at a constant rate. But then he's sprinting, so that means the distance increases at a much, much faster rate. Something like this. And again, this little smooth thing here would be like this smooth thing here, where he gets at this sprint. This is the time he's sprinting, which is, you know, this second chunk here. And maybe my time pieces don't quite match, but they're pretty close. And then when he stops, the distance remains constant. So as long as he stops, the distance is the same. And then he starts walking home, slowly home. So certainly the slope of him walking home is going to be less than the slope of the jog. And notice it's going downhill. Why? Because he was jogging and sprinting away from home, and then he's walking towards home, walking slowly home. This is what's weird, right? If I were to do the instantaneous rate of change of this chunk here, or even the average rate of change, the IROC or the AROC, they're both negative. Because the distance from home was decreasing. So if I was thinking about this speed, I could have thought of it as velocity or from home, speed is a positive speed is going away from home, a negative speed is going towards home. I could have had it this way, right? That when he was walking home, he had a negative speed, the opposite direction perhaps. Opposite direction, negative speed, maybe. I would accept both of these graphs, whether it was a positive or a negative here. Probably the negative makes more sense because the IROC and AROC would be negative there. Won't see the time. I'm going to probably have to pause and do part two. Yep, pause, part two, coming up shortly.